But go ahead.
Thank you.
Thank you. It looks like we have everybody in. Is that correct? Looks like 6.
Yeah.
Clayton, welcome.
Thank you.
I hope you got all that stuff from other people, or you got onto. I think I sent you most of the stuff anyway. But
Yes, sir. I have it all.
okay, good.
Thank you for that.
I'm just waiting for Maria to come back on to make sure that she gets the recording going. So whenever she gets back on, again, she's trying to monitor 2 different seminars, which can't be easy.
Yeah, I just want to make sure you can hear me correctly.
Mostly.
Oh, sorry, this one, mic is weird.
Yeah, it's just a little muffled. I can still understand you. Just a little muffled.
Okay. Oh.
How was your week?
My week. Well, challenging as always with the little girls, but I guess we survived.
So they haven't, I thought classes had ended. Not yet?
Oh yeah, school's over, and they remind us every day, why do we have to do this? But our granddaughters live with us with their mother. The parents divorced last year, and we just, my wife is an early childhood educator.
Yeah.
But right now she's a librarian for the Children's Museum, but she just refuses to let these kids just sit around and do nothing all day, watch TV, or their favorite thing is just getting on the computer and playing games on the computer. So we give them free time, but we also make them work a little bit just to keep their mind sharp. So
there you go. Take them outside so they can learn some geology.
Well, the older one is actually very interested in minerals and dinosaurs, and told me yesterday she wanted to be a paleontologist. And I said, well, that's a geologist too, Oh, really? I didn't know that. So if that ever happens, that'll be the first in my family. Both of my kids are basically biologists by training, and although my daughter has a degree in economics too, and but they both work in medical related or biological research related fields. So. And you guys, how was your week?
Long.
Yeah.
Slow and boring. Trying to find a job.
Yeah, I hear you. Things are sort of ticking in the right direction. It's going to take a little bit of time, I think.
Yeah.
I think people are still wondering if the price is going to stay firm or if it's not going to torpedo again when they start pumping all this stored oil, which I think could very well happen. So we'll see. Let me email Maria and see where she is. And
I'm here.
Do you still communicate with, or do you have a good relationship still with the department at Miami?
a few people. It's changed quite a bit from when I was a grad student there. But there are a few senior staff that are still there that I know well and worked under when I was a grad student. So
yeah, just wondering. I was looking at some there. They had a couple research positions open. My whole family's in Florida, so
well, that's maybe something to look at.
thinking about it. So
what are you looking at? Which programs are you looking at? Everly's?
So there was the Marine Geoscience PhD program I was looking at. I think they have 2 open positions there for research positions. And then I was looking at Oklahoma State right now, between Oklahoma State, Dr. Grammer and Dr. Bucket and the NAPS, and then and then left. I'm just kind of playing around some other schools. I'm pretty right now I really like Oklahoma State for a PhD, but just playing by ear, talking to everybody,
Well, the good thing about Miami is it's just not a modern marine carbonate school. That program dabbles a lot in the rock record. It's got a lot of ties to Europeans. It's funded by industry, so it has a lot of industry ties, and people have worked a lot of subsurface data. And in fact, a lot of students end up working subsurface data. So that would be the added plus. I mean, well, the big plus would be you would most likely see a lot of modern carbonates, both in Florida and the Bahamas. So, as you're going to see with this lecture, that's invaluable when you're trying to understand carbonate systems, if that's where you want to go. And, if you don't, if you want to go into something else, then, Oklahoma State's probably a better choice because they're going to be probably a little bit more, I don't know, they may not be diverse.
They're starting to, the my undergraduate advisors from South Carolina, they are now the directors of the program, and they're geophysicists. So my background is more in geophysics than anything else. But then working as an operations geologist and all these resource plays, all of them have some marine aspect to them, carbonate, influence, especially Eagle Ford, Bakken, even scoop stack stuff that I was working. So
okay,
all this is extremely relevant. I kind of wish I would have taken this class before starting in operations, but
good. There goes.
Yeah.
All right, hi Maria, are you ready to record? Okay, so let's go ahead and get started. So let me just start this discussion by reminding you or refreshing your memory from what we tried to do last Friday and Saturday. Basically, those 2 days were days to introduce you into how a carbonate rock is put together. We talked about the players, both skeletal and non-skeletal, their recognition, their formation, perhaps more importantly, what they tell us about the environment of deposition. And then we broadened our discussion a little bit to talk about the textures and how they reflect either depositional setting or the reservoir potential of a carbonate rock. That was a Dunham classification scheme, and it was modified a little bit by the Embry-Clovan system for reef limestones. And then we got into a discussion about diagenesis, so you appreciate where some of the cement fabrics come from, how we create the secondary porosity, some of the key controls, and what I hoped I stressed was that it's really important to appreciate the timing relationships because whether your diagenesis is early or late sort of depends on where the fluids are coming from. If they're early, they're probably tied to obviously marine or subaerial exposure surfaces. But if it's a later diagenesis, whether it involves limestones or dolomite, then most likely the fluids are coming upward from a deeper seated source, and that's where the structure comes into play. And again, if you can understand those timing relationships, and I'll try to demonstrate this when we get into our carbonate plate discussion in next weekend, I think it is, and you'll see how this all ties together. And then of course I think we finished up by just briefly talking about porosity classification schemes just to make sure you understood the terminology. All right, so everything we talked about was essentially out of context. Now we need to start adding context to our discussion. And the first thing we're going to do all of today and part of tomorrow is talk about modern carbonate environments. And the goal here is to give you a feel for the setting, some of the key controls on carbonate deposition, to give you a scale perspective in terms of dimensions, aerial extent, thickness, and things like that. But the caveat to our discussion today and tomorrow morning is that we're only talking about what we call Holocene age carbonates. So the strict definition of Holocene is the sediments are less than 10,000 years old. But in reality, because of what sea level did from about 18,000 years ago to present day, most of the sediments didn't form until we flooded the carbonate platforms, like in the Bahamas or the ramps in the Arabian Gulf. And what that means is most of our sediments are 5,000 to 7,000 years old at the most, and a lot of it's less than 3,000 years old, just because of the way the flooding of marine water over these platforms occurred. Okay, so we have to keep that in mind, and we're going to add time factor to our discussion tomorrow afternoon. When our last lecture will be on depositional sequences and cyclicity, so you appreciate how we evolve thicknesses and geometries and how these depositional faces stack together to get what we call depositional sequences. All right, so let's start our discussion with this first slide. We study modern carbonate environments for two major reasons. The first is it helps us relate the facies attributes, the texture, the fauna, the porosity, and the geometry to the depositional setting. And we really didn't start studying modern carbonate environments until about the mid-1950s. And most of the initial emphasis really didn't start until the 60s and 70s. And people are still working in modern, still discovering new relationships. So we haven't learned everything yet from these modern carbonate systems. And it's really now what we've learned from the modern that provides the guidelines for predicting these facies trends in the subsurface. This is basically the basis for what I said were the two N-member models that we use in carbonates to better understand the distribution of facies in the subsurface. On the one end of the spectrum is the steep margin platform system, like I'm going to talk about quite a bit today for the Bahamas. And then on the other end of the spectrum, which I'll talk about tomorrow, is the carbonate ramp model, where by definition, the slope angle from land to the basin is only about 1 degree. Okay, and those are the N-member models. You change the slope angle a little bit, the facies relationships can change along those depositional profiles. But we need something to guide our interpretation of the subsurface, and we rely very heavily on these two N-member models. And we do this better now because of this concept of comparative sedimentology, gleaning relationships from the modern and applying them to the rock record. Again, if you look back in the old literature back in the 40s and 50s and compare it to what we know today about carbonates, I mean, it's just like night and day, right? Because nobody had studied modern carbonate systems up until the 50s, and we really didn't understand what controlled the occurrence and distribution of these older carbonate systems. So I've been using this term facies, and I just want to caution you here that the term facies really should be used for a rock and not for a sedimentary environment. But I think we all fall into that trap of doing that. And you'll hear me talk about oolitic sands or tidal flat facies and things like that. The strict definition, I've given you a bunch of definitions here for the term facies. What the term facies is not is a lithological descriptor. So grainstone is not a facies, packstone is not a facies. Okay, basinal limestone is a facies because it tells you where the rock or sediment accumulated. A tidal flat packstone is a facies term because it tells you where your deposition occurred. So the goal here toward the end of our seminar is to be thinking in those terms. What does that rock tell us about the depositional setting? Can we place it into part of one of those M-member models? So the simple definition is the one that I offer here at the base of the slide here. What is a facies? It's a aerially segregated body of sediment or rock that basically reflects a depositional environment. So if you just think in those terms, I think that'll make it easier for you to understand what we're trying to do, right? And again, I showed this slide when we started last Friday, just to remind you again that all of these carbonate systems that we study today in shallow water are mostly confined to tropical, subtropical settings. So that's from the equator to about 30 degrees north or south of the equator. We talked about what comes along with that in terms of water quality and trade winds. All of these environments, again, are supersaturated with respect to calcium carbonate. The water obviously is warm. It's usually clear, free from much solicitoclastic sediment influx, especially fine-grained clays. That's really what's detrimental to carbonate production. If you cloud up the water column, you shut down light penetration, which is obviously detrimental to many of these organisms that need light or have a symbiotic relationship with organisms that need light, like I mentioned for the corals. But as I said the other day, north or south of 30 degrees latitude, we get into the cool or cold, so-called temperate water climates. You can get some carbonate deposition there, and we'll talk about that tomorrow afternoon. I said I wouldn't test you on the cold water, temperate water carbonates, but I will give you a lecture just to let you appreciate the major differences between what we see in these cooler water climates and what we see in the warm tropical, subtropical settings. Now you'll notice on this diagram, there are some light green areas off of West Africa, for example, where you do get cool water carbonates. And the reason for that is you get upwelling. Upwelling always occurs on the leeward sides of these steep margin carbonate platforms or continents, all right? So you do the same thing off the Western US. You see that here, the light green. And some of this is still in a tropical, subtropical setting. But this is pretty minor, all right? Most of what we see today is in settings greater than 30 degrees latitude. And as I said the other day, I ignore this stuff for the most part because I don't know of many actively explored basins in the rock record that fall into this cool water setting where paleogeographically we can show that they were outside this belt of 30 degrees to 0 degrees latitude. Okay, but we will formally talk about this briefly tomorrow. And again, I want to remind you of what I showed you before, the trade wind influences. They always come along with the tropical, subtropical setting. Our frame of reference should be the equator. And
I have a question.
Sure.
Yeah, in the previous slide, what were the blue shadings? Were those like lakes or freshwater?
Yeah, that's all it is. Just freshwater lakes.
All
So
right.
the Great Lakes and Straits of St. Lawrence, and then these lakes in Russia. That's all. Sorry. Yeah, I mean, from a carbonate perspective, the interest to us would be the dark green is the deep water pelagic carbonate, the light green is the cool water carbonates that tend to, as I said, can occur both on the leeward margins of these steep platforms, so they occur in latitudes greater than 30 degrees. And then the black dots are modern day reef systems, and then the red would represent shallow water carbonate platform systems. Okay, and you can see most of those are, again, limited to that belt between 30 degrees north and 30 degrees south. Okay. The trade winds, again, I mentioned, prior to the late 80s, we really didn't appreciate the role that these trade winds played. Not until we started doing research in the southern Bahamas, the windier, stronger easterly trade wind systems, did we realize the pronounced influences of the trade winds, not only in influencing the styles of shallow water carbonate deposition, but in modifying what gets shed off the edges of some of these carbonate platforms. And I think I sent you a copy of our paper that we finally published in 2017, sort of summarizing most of our research on Caicos platform. You'll hear me talk a lot about Caicos platform today in contrast to the northern Bahamas. And basically, that's what we're going to end up doing is contrasting the general easterly trade wind belt in the northern Bahamas, which is the basis for most of our popular steep margin platform models, and then comparing it to the windier Caicos platform in the southern Bahamas. And I'll obviously build on this as we get into the rock record and talk about how we can recognize geologically the influences of these trade winds. And this has significance from a place standpoint that I'll build on, I think, starting next weekend. So just to remind you, the belt of tropical, subtropical deposition occurs from 30 degrees south to 30 degrees north of the equator. But I said last week that right at the equator, 5 degrees on either side, are the doldrums, where the trade winds don't blow. And as you'll see later, hurricanes don't come into the doldrums because they're pushed by the trade winds. So you never get a hurricane effect right along the equator if you're 5 degrees, roughly 5 degrees on either side. And then from 5 degrees north to about 21, 22 degrees north or south, so 5 degrees to 21, 22 degrees north or south, that's a strong easterly trade wind belt. What that means, again, is the winds blow more persistently and stronger during the year, but they don't just blow from an eastern quadrant. They can have a southeast component moving up to the northeast. They can have a northeast component moving to the southeast, okay? And as I said last weekend, that can vary from month to month or from year to year, okay? And so that can have at least some short-term effect on your styles of carbonate deposition, as you'll see, even movement of some of the carbonate sediments on these platforms. And then when you go to 21, 22 degrees to 30 degrees, you still have the same wind patterns here, but the winds are not as strong and they don't blow as persistent. So they have less of an effect on some aspects of shallow marine carbonate deposition compared to the windier systems, okay? And then, of course, when you go north of 30 or south of 30, as I said before, not only are you in the cool to cold water environments, but the winds shift now from the west. So this is what we call the westerly wind effects, all right? And the other part of the story we're going to develop tomorrow will be the effects of hurricanes, because hurricanes come along with that tropical to subtropical setting. They're not limited to that setting. They can move north or south from there and actually affect some of the cool water carbonates, but usually they don't. Usually they die out before they get into the cooler water carbonate settings, because cool water is detrimental for fueling the hurricane, right? You need that warm water to help that hurricane thrive, okay? So I'm going to spend a lot of time today and tomorrow talking about areas like the Bahama Platform Complex. The city of Miami is where I'm pointing with the arrow. It's right over here. There are shallow water carbonates that occur in the south of the Florida Everglades and in the Florida Keys. We're not going to talk about these in any detail for this seminar. They're sort of a modification of a theme, sort of a unique setting when you think about it compared to the classical end member models that I'm going to discuss for this seminar. But you look at all the light blue areas here. These are all the areas of shallow water carbonate deposition. The yellow features are islands in the Bahamas. All of these islands are Pleistocene or a little bit older, and we don't actually know the full age of some of these islands because it's very difficult to age date these carbonates once they get altered by the freshwater diagenesis we talked about last week. But you can see there's a scale here. So let me put this in perspective. This is about 300,000 square kilometers of shallow water marine carbonate separated by extremely deep water basal environments. And by extremely deep water, we're talking 1,000 over 3,000 meters of water depth. Okay, so that has an effect on the styles of carbonate deposition, and we'll develop that. And you can see in the Caribbean, there are other areas that have been studied historically. Old studies back in the 50s that documented some of the shallow water carbonate deposition on the southern side of Cuba. More recent studies done off in Nicaragua and Honduras. The famous barrier reef, the best developed barrier reef in the Caribbean, is off of Belize in this position right here. And we will talk about the Belize model and contrast it with the more extensive and more famous Pacific reefs like the Great Barrier Reef later on. And then there's a relatively broad area, Campeche area over here, Yucatan bank area that has some shallow water carbonate deposition that's been documented in the literature. But most of the studies have been done in detail to document these sedimentary environments in terms of their setting, their controls on deposition, the resultant sedimentary products, their early diagenesis, all come from studies done in this part of the Bahama Platform Complex. Okay, and from a physiographic standpoint, if you put the Atlantic Ocean back together after it started spreading late Jurassic, early Cretaceous, the Bahama Platform Complex basically would stick back into part of Europe. So because of that, people think that the platform system really didn't develop until after that initial rifting to set up the Proto-Atlantic. And nobody really understands the roots of the Bahama Platform Complex very well, but everybody suspects the southern platforms are probably underlain by oceanic crust. The northern platforms are underlain by continental crust, because we have some really deep drilling that's been done in South Florida that shows at about the same latitude that the southern tip of Florida is also underlain by continental crust. And probably a lot of these platforms developed because of horse and graben development, sort of the typical structural expression you get when you start rifting and developing these big ocean basins. Okay, So the beauty of going to the modern is that we know our setting. And remember, I've defined physiographic setting to two scales. The first scale is our global scale. Where does our point of interest sit relative to the equator or paleoequator? And then on a local scale, where do we sit along a depositional profile? So where do we sit along a platform to basin transition? Where do we sit along a ramp to basin transition? And of course, that controls water depth, right? That determines what your starting water depth is for, and that's obviously a key control on carbonate deposition, as we talked about last week. Remember, most of our shallow water, what we define as shallow marine carbonates are in water depths by definition less than 10 meters deep. And as you're going to see in this discussion today and tomorrow, most of these environments are almost stand-up water, right? 2 to 3 meters of water depth at the most, a lot of times less than 2 meters of water depth. So obviously we can tell from the clear water that how deep we are, whether we're in a few feet of water, whether we're in 40 or 50 feet of water. I guess we can stick our tongues out and evaluate the water chemistry, but we have obviously tools to do that, to measure things like salinity, saturation state, alkalinity, things that might tell us how prone an environment is for precipitation by physical chemical precipitation. You will know the water energy in the settings you visit, whether it's quiet water, whether it's energetic. Is it energetic because of strong tidal currents? Is it energetic because of breaking wave energy? Is that breaking wave energy due to the stronger trade winds, or is it due to oceanic swells? And then obviously you can evaluate the substrate type if it's not too deep and tell whether it's a sandy substrate, a muddy substrate, or a hard substrate. As we talked about before, that's important for controlling the occurrence and distribution of some of the skeletal producing organisms. As you saw last weekend, right? Some organisms prefer hard substrate, some prefer to live in sand, some prefer to burrow in muddy substrates. And of course, we can measure in the field the starting processing permeability. I showed you those numbers last weekend when we started our discussion of limestone diagenesis. And of course, we can collect samples and run it through the X-ray diffraction machine and figure out how much aragonite material is being produced, how much high mag calcite, how much low mag calcite, and that has a bearing on the diagenic potential of that environment, right? As we talked about last week. At the same, basically, these are the controls on carbonate deposition. Okay, so you can evaluate these in the field. At the same time, being in the field, you can collect the samples, you can evaluate texture, composition. I showed you how we core in some of these environments with the metal aluminum irrigation tubing. We can extract those and actually see the sedimentary structures that are preserved. We can vibrocore the sandier substrates and see the sedimentary structures. And then we can shoot high resolution seismic on the seafloor and get a feel for geometry and orientation. That's the beauty of working in modern, okay? But again, the limitation is the age represented by those sediments, right? It's not very much. Now you go to the rock record, what do you have to work with? You have some of this to work with, right? You drilled a well, maybe you shot some seismic, you drill a well, maybe you cored, and so you can evaluate samples from the core. You can see what the texture is, the composition, the sedimentary structures. This is what we have to use to backtrack to figure out what our depositional setting was. And we do this better now because of comparative sedimentology, okay? And that's why I'm going to spend so much time talking about modern carbonate environments, so you appreciate how we use this information to build our depositional models or to make a more, I think, accurate interpretation of our depositional setting. Because this is always the challenge, especially with your first data point, right? The first well you drill, the first core you take, you get what, 3 or 4 inch wide rock to look at, might be 60 feet long, it might be several hundred feet long, and you got to work that and try to figure out where you're at. And sometimes you can't figure it all out just from that one data point, but at least you can do it better, I think, because of if you can apply some of the comparative sedimentology relationships we're going to talk about today and tomorrow. Okay, and so let me remind you again of our general carbonate settings. Today we're essentially dealing with oceanic settings. All of these shallow water carbonate platforms we have in the Caribbean or Pacific front a really deep water basin that is thousands of feet thick to over 10,000 feet of water depth. Most of our basins in the rock record were associated with these isolated intercantonic basins or broad epoxic seas, like we had in the Ordovician, extending across most of the continental U.S., or these broad epoxic seas that we had in the Upper Cretaceous that extended from the U.S. Gulf Coast all the way up to Western Canada. The hydrography, or what we call the water circulation, is going to be different depending on those gross depositional settings, okay? And then the other considerations I said are the 2 member models. Is it a steep margin platform dropping off abruptly into a deep basin, or is it a ramp? That controls not only water depth, it also controls water circulation along that depositional profile. And then, as I said the other day when I got into our discussion of diagenic environments, I said, we used to look at climate just from the standpoint of rainfall. Are we in a dry climate with low fresh water? Are we in a rainy climate, humid? But now climate also entails the influence of these strong to weaker prevailing wind systems from the eastern quadrant. And so that has an effect on carbonate deposition as well. And I think I can demonstrate that to you when I take you down to Keiko's platform later today and tomorrow, okay? So this is a sort of a generalized cartoon that illustrates the 2 member models that we use or deal with in carbonates. On one extreme, our shallow water carbonate platform dropping off into a very steep angle into a relatively deep water basin. Again, the basin is defined as generally being hundreds of meters to several thousand meters of water depth. The slope angle, the average slope angle can be up to 45 degrees. That's usually never more than about 45 degrees at the steepest, although the first 200 meters could be 90 degrees, right? A vertical wall. If any of you have done diving in the Caribbean, people want to go dive the wall. So they dive the upper 200 meters because it's a vertical wall, but then it splays out, right? And it ends up with an average slope angle of about 45 degrees. That's usually the typical steepness of the platforms that face into the open ocean sides of these basins or the windward facing sides of these basins. When you get on the protected side, right, a leeward side or leeward with respect to the open ocean, the slope angle is much less. It's only 7 to 10 degrees or so, okay? So keep that in mind when we evaluate some of these models and also the occurrence of some of these carbonate environments. And you can see that the lateral scale here can be quite variable. And then on the other end of the spectrum, as I said, is the carbonate ramp. And again, we always steepen the angle here to fit everything in. But by definition, the slope angle is 1 degree or less. And the basin or deep water part of the profile out here is really shallow compared to areas like the Caribbean today. The only analog we have of a ramp today in the modern, really, that's well documented, is the Arabian Gulf or Persian Gulf in the Middle East. And there, the deepest part of the basin is only 80 meters, roughly 240 feet of water depth, which is not very deep when you compare it to the steep margin platform systems I'll show you from the Bahamas, okay? Now, we've learned, though, that this is not good enough. We can't just look at the context in terms of these 2 member models. We also need to start thinking about our orientation with respect to the trade winds, which will always come into play for any system, right? When you think about it, even the westerly temperate water systems, right? Some parts of these areas of shallow water could face into the stronger prevailing wind. Other parts could face away, right? So in a tropical, subtropical setting, not only are we concerned about our carbonate ramp, does it face into the prevailing wind? Okay. Is there a windward side? Is there a leeward side? There would be a leeward side if that platform was detached, right? And you have deep water surrounding the whole platform. Ramps have to be attached to a land mass, so they're either going to face into the wind or they're not. They're not going to have a leeward windward side. It's going to be one or the other. But like I said, I'm going to show you isolated carbonate platforms in the Bahamas that are surrounded by really deep water. So it makes a big difference whether you're on a windward side or your leeward side. That controls the styles of carbonate deposition on the top dependent in part on the strength of the trade winds, and then dependent in part on the strength of the trade winds, it also has an impact on what kind of sediment gets shed off. And what side do we preferentially shed? We preferentially shed off the leeward sides, not the windward sides, okay? You will shed material. I mean, a hurricane can hit a platform any way it wants, and it can shed in any direction. But typically, and I think this will become well expressed when we get into the rock record and we talk about case studies, you're going to see that most of the shedding in these isolated carbonate systems tends to occur off leeward margins, okay? And the question is going to be, what's the composition of that material? Is it very grainy with good reservoir potential, or is it more micritic? So that's the thing you need to evaluate, okay? So what we're going to do here, and we're going to take a little break here in a little bit, but I'm going to start with this sort of generalized carbonate cartoon that shows you platform to basin transition, all right? And shallow water carbonate platform dropping off in a deep water basin, and basically this shows you potentially all the different styles of carbonate deposition you can get along this carbonate platform. But the other control here is the age of the sequences you're talking about, okay? For example, pinnacle reefs, which are common in the lower Paleozoic and the Silurian Devonian, they reappear in the Jurassic, they obviously reappear in the Tertiary, don't exist today, okay, in the modern. And the reason for that is our basins are too deep, okay? They couldn't get started in deep water. There's some low relief mounds that are developed. If you go to, there's literature from the Straits of Florida between the Bahama Platform Complex and Florida that show these very low relief buildups starting to develop, but they have no scale at all vertically compared to the classical pinnacle reefs, which ended up with anywhere from 600 to 1,000 feet of vertical thickness, okay? So you have to factor in the age here because sometimes these depositional settings are not really conducive to in situ carbonate production because you didn't have the right kind of organisms or the water depth was too deep. But in the basin, you can have obviously a background of pelagic carbonate deposition. If you're in Mesozoic and younger systems, I mean, principally upper Jurassic to younger systems like today, we have this constant rain of pelagic carbonate deposition that we talked about last week. We call the planktonic foraminifera, the coccoliths, and things like that. And then that's going to be periodically punctuated by whatever kind of material you can shove from the platform into the deeper water. That could be fine grain carbonate material, that could be coarser grain material. We can sometimes produce turbidites, sometimes I think more typically we produce grain flows or rock flows and things like that, of course, are reef derived material. But that can punctuate this deeper water setting periodically. And as I said, pinnacle reefs can pop up in this position. Normally they don't occur in the deeper parts of the basin. They often occur in this transition zone between the slope into the basin, but not in too deep water. As we'll talk about when we get into plate type discussion of pinnacle reefs, most of these pinnacle reefs are nucleated by some structural influence, reactivated basement fault or some fault influence that kicked off some style of carbonate deposition that created topography, and then that reef took off from that pre-existing topography. Of course, we can plaster some of this shallow water material along the edge of the platform, produce these onlapping wedges that have exploration potential. Historically, most of what we've explored for in the rock record has been focused up on the platform, and most of it's been focused along the platform margin because we can usually recognize that frame of reference from even 2D seismic data. And so people historically played either for linear high energy reefs that develop in this position here, or they play for carbonate sands, sometimes linked to the reef or sometimes not tied to the reef. For example, oolitic sands would occur in a position like this potentially. And then platform materials you'll learn can be high or low energy depending on the depth of the water and whether we have these trade wind influences coming into play here. So platform material can be carbonate sand prone or it can be carbonate mud prone. It can be punctuated by generally low relief buildups, again, taking advantage of pre-existing topography. Again, in the modern, that would usually be related to karst topography that was created during the last low stand when these platforms were exposed so early and underwent some karsting. And then, of course, along the shoreline, we either get tidal flats developed in a position like this, or we can have beaches obviously developed in a position like this that are sand prone, again, if you have the right kind of energy to win out the micritic material and concentrate carbonate sand. Okay, so this is sort of a catch-all cartoon. You'll actually see this again when I introduce you all to our discussion about carbonate plate types. And again, I want you to appreciate the potential. That doesn't mean that for every age sequence we look at in the rock record that you're going to get potential plate development everywhere along this depositional profile. For some of the reasons I already said, right? It might be the wrong age to have things like pinnacle reefs, or it might be a part of geological time where we didn't have good shallow water reef deposition, right? Like in the Pennsylvanian and Mississippian. So you're not going to get platform margin reefs, you're going to get some other style of high energy carbonate deposition. Okay, so age is part of the story. Age is what we're going to factor into our discussion about carbonate plays when we get to that part of the seminar later on. All right. Any questions about anything I've said so far?
How do those? What's the main way those pinnacle reefs start to form, or the main driver for those?
The main driver is usually some pre-existing topography. And before we had 3D seismic, it was hard to see on 2D seismic what was initiating the initial topography. But the 3D seismic that's been shot, excuse me, over some of these fossil pinnacle reef shows that it's reactivated basement faults that provide the initial topography. And then things like crinoids or deep water corals come into play and they make these low relief mounds that accentuates the topography. And then whatever makes the pinnacle reefs, whether it's corals or stromatoporoids, they take off from that. Okay, and they just start shallowing up, and they will actually sometimes build all the way to sea level. And we know that because they're capped by beaches or tidal flats. And you can't do that unless you build to sea level. Okay, so what I'm going to do now is I'm going to give you an overview of modern carbonate environments, and I'm going to start in deep water and just talk from a few slides because I mean I could pull a bunch of stuff from the literature, none of which I have personal experience with, but from people who've been down in submersibles and things like that and show you what things look like. There's lots of documentation of the deep water settings from in APG Memoir 33, the book I mentioned last week. So if you want to see pictures of underwater pictures of the deeper parts of these basins, that's a good place to go. I'm going to sort of work backwards and show you examples of basinal limestones and show you how we try to figure out what the nature of that depositional environment was. And then we're going to move up on the foreslope and I'm going to talk about the processes that operate there and some of the controls. And then most of our discussion today and tomorrow is going to be focused on the platform itself. We'll start first with the general platform margin settings. We'll talk about linear reefs that we call barrier reefs, and we'll contrast settings so you see how the settings have an impact on the way these reefs are put together. And then we'll talk about oolitic sands that form along the edges here. Historically, we used to think that the only way to make ooids was with strong tidal current agitation. The strong tidal currents only occur along steam margin platforms, all right? So you're forced to just limit your exploration to that kind of setting. But we've learned now with the strong trade wind systems that you can make ooids well up on the platform. Now, you're going to see examples in the rock record of being well over 100 miles inboard from the open ocean where these older ooid sand systems develop because of the effects of these stronger trade winds, okay? So that's pretty neat because it expands our potential for exploring for those kinds of high energy grainstones. So I'm going to contrast two ways to make ooids. The classical model is the strong tidal current effects, and then I'm going to take it to Caicos and show you how strong trade winds, agitate the water persistently enough to make ooids as well, and produce sand bodies that are of comparable scale to what I show you for the tidal current systems, okay? And then we'll talk a little bit about the platform interior styles of deposition, both for the windy and non-windy systems or less windy systems. And then we'll finish up by talking about tidal flats that occur at this transition between shallow subtidal and an older landmass, okay? The older landmass may be an island that's 500 years older than the stuff that's being produced offshore, or maybe a Pleistocene island, or maybe a granitic feature that was inherited from basement topography. Okay. All right. So let's start with a rock like this. All right. And so you see a sample from 1,100 meters of burial. This is from Western Canada, the Duvernay Formation, or Duvernay, depending on which Canadian you ask, is a major source rock in Western Canada. It's a major carbonate source rock for all the oil and gas that's produced in Devonian, Mississippian carbonates, and even in some of the younger Jurassic and Cretaceous classic sequences. And so what do we have to work with here? We have this piece of core. You can see it's darker colored. You see the 8% TOC. We talked about this before. That's the total organic carbon, which is a proxy for its ability to yield hydrocarbon. 1% is pretty good. 1 to 2% is sort of the standard for a good shale source rock. So this is excellent quality from a carbonate source rock perspective. And then what's our sedimentary structures here? Planar, parallel laminations. All right. And so what were the two ways we talked about last week to preserve this? What do you need to do to the water to preserve stratification like this?
But low energy.
Well, obviously slow energy. Okay. I mean, and I told you it's basinal, so we know we're in relatively deep water. But what else? What else do you have to do to water quality? In other words, the question is, why isn't it burrowed?
Oh, and
it's low oxygen and salinity.
Right. It's either low oxygen, which we define as being anoxic, or it is hypersaline, right, where the salinity of the water is so high that even soft body worms could not live in this environment. Here it's probably anoxia because there's no evidence of syn-depositional evaporite deposition associated with this, which would oftentimes you would get with a more hypersaline basin. Okay. All right. And then all of this rock is micrite, or 8% organic material. Where's the micrite coming from? Well, let me rephrase that question. Is it coming from the overlying water column, or is it coming from nearby carbonate platform?
water column.
And what would produce it in the Devonian from the water column? This is where you have to factor in the age. So in a basinal setting, in our younger carbonate systems, right, Jurassic through modern day, what lives out in deeper water in the upper part of the water column? The pelagic microfossils, remember the forams, the calcospheres, and then the nanofossils would be the coccoliths, right? Remember the little one that a few micron across size, little spokes of the wheel, pieces of calcium carbonate. Remember those critters? They're produced from the golden brown algae. But we're in the Devonian. They don't exist in the Devonian, okay? They don't exist in any Paleozoic rock that's been discovered so far, all right? So you can't source this material from stuff living in the upper part of the water column that produces mud-sized material and then settles down, okay? So where does it have to be coming from?
Solution, the water column.
It has to become, yeah, it's from the water column, but where initially was it derived from? The adjacent carbonate platform, right? It was pushed offshore into deeper water by big storms. I'll show you pictures of this from the modern after hurricanes. I'll show you this tomorrow, okay? And once the stuff is put into suspension, it'll stay in suspension for days or weeks, and it will be drawn offshore by normal tidal current movement. And then what happens? It just settles out, right? And if it settles out into an anoxic environment, then you produce the sedimentary structure you see in this view here, okay? And if this is your source rock too, then you need to think about, well, what's the geometry of this material that's being moved from shallow water platform out into deep water? What would you expect? If it's linked to the platform, you would expect it to be thick up against the platform, right? Thick up against the platform, and then to do what? Thin and pinch out into deeper water, right? See the implications for basin fill in the Paleozoic. It's always more of this sort of onlapping wedge-like geometry, right? It's always going to be thicker up against the platform, closest to the source of this fine-grained material, and then it's going to thin out or shale out into the deeper part of the basin, okay? So that's a characteristic of many Paleozoic basinal limestones, whether they have organic potential to be source rocks or not, okay? Now, contrasted with a younger basinal limestone, this is the Austin chalk. I showed you this core last Saturday morning when we talked about sedimentary structures. I said these are the byproduct of burrowing shrimp. So technically, this is the lacinoides fabric, but in the chalk, it's also called a ring or rind burrow because of the oxidation halo that they create. And they do that by pumping oxygenated water into their burrow structures, right? They can sometimes go down meters below the sediment water interface. And so not only are they burrowing the sediment, obviously, but they're bringing oxygenated seawater. So the net effect is a very low TOC, no source rock quality as soon as you get burrowing, okay? So obviously what's different about this basinal limestone is it's bioturbated, which explains the lighter color and the lack of high TOC. And then the question again is now, what is the likely geometry of a Mesozoic or tertiary age basin fill limestone? Is it going to be wedge-like where it's thick up against the platform and thins? Or is it going to be more sheet-like and widespread? Again, what is producing the micrite in the sediment now that we're in a younger Cretaceous system?
The organisms?
Right, the pelagic organisms, the ones that lived in the upper part of the water column. They're raining this material down constantly. So a mixture of planktic forams and then nanofossils that we talked about before. But there still could be contribution from the adjacent carbonate platform too, right? Because all of these basinal settings will be linked to a shallow water setting. So typically the geometry for Mesozoic and tertiary age basins of carbonate are more sheet-like, right? They're widespread all the way across the basin because you have this constant rain of pelagic material. Unless you can somehow inhibit that constant rain. And how would you do that? Anybody know? What would be detrimental to the production of coccoliths, for example?
Available bicarbonate in the water column, or the ability to precipitate out a solution to create their shells?
Well, I mean,
Like
if you're in a tropical subtropical system, that's going to come along with that anyway. What's the organism that produces coccoliths? It's called golden brown algae. What do algae need to live?
sunlight.
Sunlight, right? They need sunlight for photosynthesis, right? The photosynthesis plays a role in the carbonate production. So imagine if you have a basin, and one side there's no river input, on the other side you have a Mississippi River kind of system, a delta feeding in pretty persistently coarse and fine-grained clastics, right? You're climbing up the water column on one side of the basin. That'll be detrimental carbonate production by this mechanism, all right? So you could end up with this, not a sheet-like geometry, but more of a wedge-like geometry where it pinches out because of that persistent clastic influx on the other side of the basin, okay? I mean, that's what's happening today off of Mississippi River. You don't have good carbonate production. I mean, it's very difficult for carbonates and clastics to coexist together if you have persistent fine-grained clastic input, right? It's really the fine-grained stuff that's bad. Clouds up the water, inhibits light penetration, or if it was a filter-feeding organism trying to live on the seafloor, the clastics would do what? They would basically kill most of the organisms. Oyster could probably handle it, right? It would filter feed and remove the clastic material, but most organisms, they can't do that. They're carbonate producing. Okay? So this is where the age comes into play. You got to think about the age when you're evaluating these systems and who the constituents were that produce sediment out in deeper water. So Mesozoic and younger systems, as I showed last week, it's the pelagic or planktonic microfossils, the globose, planktic foraminifera. They're almost always less than a millimeter across for size. They're low mag calcite and very good potential to be preserved in the rock record because of that low magnesium calcite mineralogy. But then the macritic matrix that you see in this thin section is made up of what? It's made up of the golden brown algae, the byproduct of golden brown algae deposition, the cocosphere, the armored ball structure in which the algae lived, and then the individual plates, because usually this breaks down into the individual plates that are called coccoliths. Okay, and they too are stable low magnesium calcite, the most stable form of calcium carbonate we have, right? We're not talking about dolomite, we're just talking about calcium carbonate. Okay, as we talked about before, aragonite is a much less stable, much more unstable form of calcium carbonate. All right, and then that's all I want to say about these basinal settings. We will talk a lot about basinal carbonate plays and evaluate different styles of deep water carbonate play development. Basically, they now fall into the category of what people call unconventional carbonate plays. And I characterize that as unconventional anyway, because historically companies haven't chased that kind of setting for play potential. Of course, that's all changed now with the fracking technology, right, to go after the carbonate, the organic material that's tied up in a lot of these pelagic carbonate systems. All right, so let's move up onto the slope. All right, the 4-slope setting here, this transition zone from deep water, represented by gray here. This would be the pelagic carbonate material. Just for point of discussion here, let's just assume the gray are these pelagic wacky stones and lime mudstones. And then the brown here would be the carbonate platform. So the blue represents this transition zone. We come off a platform. Again, the slope angle can vary from, as I said, an average of 45 degrees to only 7 to 10 degrees, depending on what side of the platform you're on. And so what you see is you start to come up toward the edge of the platform. If you were to take a core out here at the base, you would see this interplay between gray pelagic carbonate material and blue here would represent shallow water carbonate material. This could be fine grain or silt-sized material, even sand-sized material. And so you have this interplay effect. And then what happens as you come up, you start picking up coarser grain fragments here because you're getting closer to the edge of the platform. And coarser grain could be sand-sized material, or it could actually be blocks the size of houses where parts of reefs have swelled off and rolled down the front of that slope out into a little bit deeper water. All right. And there's no scale here. I mean, the scale of some of these thin beds could be centimeters, but as you're going to see when we get to the plate type discussion, sometimes the scale of these coarser debris beds could be anywhere from 3 or 4 meters to 10 meters thick or more. And probably that is not one depositional event. Have you all heard the term amalgamation, where you shed material into deep water, right? You bring in fine grain. Well, basically what comes in first is, first thing that happens is that storm effect will strip off any carbonate material that you've laid down in the previous event. And so usually that means you'll strip off micrite and maybe cut into some of the sand that was deposited in the previous event. And you will do what? You'll put sand on top of sand with a mud drape. And the next storm will do the same thing. And that's how you build up these thicker accumulations of carbonate sand or debris or sedimentary breccias, like I'll show you when we get into this plate type. Okay. And so we expect to see that. We expect to see an increase in thickness as we get closer and closer to the platform edge. All right. Now, in classics, what is your normal means of shedding material? The normal means is to do it by what we call point sourcing, right? Have a submarine canyon that's been cut into the platform, perhaps during low stand of deposition, and then just feed that material out during low stands into the deeper water setting. But as I alluded to last week, and I'll try to convince you of this with data from the Bahamas later today, what is the shedding that we see in most carbonate systems? It's during high stands. And it's line sourcing, right? Because the whole platform edge, the whole platform is completely flooded by high stand conditions, right? So that means not only can we shed along the edges, but we can shed from back here. A major hurricane can pick up sediment from back here, it can be miles inboard from the platform margin, and put in suspension and bring it over the edge, all right? So we end up with line sourcing. That's the norm for carbonates, not point sourcing like you typically get in carbonate in plastic systems, okay? Again, an exception for high stand shedding in classics would be the La Jolla Canyon that I talked about off of San Diego, right? The famous Scripps Research Institute is right very close to the La Jolla Canyon, and that stuff is still shedding coarse grain classics out into deep water, even though it's still a high stand setting, all right? So the kinds of processes that operate in a 4-slope setting are shown here. I've highlighted in red the more typical styles of deposition we get. If you're dealing with reefal deposits, it's the rock falls where parts of cemented reefs actually break off. Earthquakes will shake the margin, cause some of the stuff to fall off because reefs create their own stability. They often get marine cemented, right? They turn into more massive blocks of reef debris, or reef material, and that stuff can be shaken by earthquakes and then fall off and move down slope. Or reefs will shed the coarser debris flow. Remember the terms we talked about last week? Float stones and root stones being shed into deeper water along with grain stones or pack stones. Grain flows are more typical if your platform margin face uses high-energy sand body systems. That can be oolitic or skeletal or a mixture of both. There are just a few examples of turbidite deposits in the realm of carbonates, and most of these are relatively young. Been documented from the Pleistocene off of the Bahamas, where people have piston cored the levees of some of these channels that go out into deeper water. I know one example in the Devonian, I think in Nevada, where they've actually documented a complete boundless sequence in some of these turbidite debris flows, but usually you don't get the complete boundless sequence, right? So that if you don't get that, then you shouldn't call these things turbidites in the world of carbonates, right? Usually they get amalgamated. You keep stripping off parts of the pre-existing sequence and you put the coarser grain stuff on top of the coarser grain stuff. Okay. Again, the timing relationship. Again, this will be the last slide here. We'll take a little break. I showed this in our discussion about carbonate diagenesis, the high stand versus low stand shedding relationship. The carbonate systems behave basically 180 degrees out of phase with the clastic system. As we said before, when you have a high stand situation and you have a clastic dominated shelf, you tend to pond the coarser grain clastics up along the inner part of that shelf. And you tend not to shed a lot of material into deeper water. It's during the low stands when you drop sea level below the shelf edge. This is basically what Exxon would call their type 1 nonconformity, right? That's when people think you shed most of your coarser grain clastics out into deeper water. Bring it out by rivers, bring it out by wind, and deliver it to deeper water, right? And I don't think anybody has a problem with this, right? It's not unequivocal for the reasons I just said, right? San Diego, you see shedding during high stands of coarser grain material. But the norm in carbonates, and this is completely opposite of the Exxon sequence stratigraphic model that they published on back in the 80s. They treated carbonates and clastics behaving the same way. There was a political reason for doing this. And we'll get into some of this discussion tomorrow afternoon, but they wanted carbonates and clastics to behave the same way to sea level changes because Speedvale was convinced that sea level was the main driver for all sedimentation, whether it was clastics or carbonates. But in reality, it's just the opposite, right? Most of the shedding in the carbonate system is during high stands when the carbonate machine is going full blast. Then the major storms, hurricanes, typhoons, tsunamis, will move material from the tops of platforms and bring it out into the basin, plaster it up along the platform margin, produce these thicker high stand on-lapping wedges that have reservoir potential. And there are a number of famous reservoirs where that is the case. If you drop sea level first, what do you do to your carbonate production? You basically shut it down, right? These carbonate organisms are going to die when you expose them to a drop in sea level. That's the first thing that happens. And then what was the second thing that happened very quickly, especially where you have a lot of aragonite in the system, very quickly, this stuff will be cemented up, right? And so typically at exposure surfaces, we don't have good rivers developed, we have karst developed, right? Karst topography, where the water wants to go from the top of the exposure surface downward. So it's hard to erode material and bring it out to the edge and deliver it to the basin, okay? Now that happens sometimes right here where waves will rework some of the cemented platform material, and you will get shedding of blocks of material out into deeper water. But you're not delivering the finer carbonate sand material, which usually makes up the better reservoir potential. You're doing that in the high stand situation, okay? And I'll prove this to you tomorrow afternoon when we summarize the models from the Bahamas and show you the first database that proved this concept of high stand shedding. And shame on Exxon for ignoring that data. It had already been talked about. Talks had already been given at meetings about this relationship, but they chose to come up with a model that basically treated carbonates and clastics the same way to these sea level changes, right? Essentially, the reason why I'm going to spend all this time today and tomorrow taking you through modern carbonate environments is to convince you that sea level is not the major driver for carbonate deposition. It's the local environmental conditions, water depth, circulation, right? Things like that, the water chemistry. These are the key controls on carbonate deposition. Sea level plays a role in either providing the accommodation, or what people used to say accommodation space. I've been lectured by sequence stratigraphers not to say accommodation space. They claim it's redundant, but most of us were initially, that's the term we were exposed to, right? Accommodation space. That provides the accommodation space, but how you fill it up has nothing to do with sea level history or sea level per se. It has to do with the environmental changes that come along with those environments you created by that change in sea level. And of course, drops in sea level terminate carbonate production. That's one way to terminate carbonate production. And then that leads to the next cycle of carbonate deposition. All right. Any questions? This is probably a good place to break. It's 2:10. I think I scheduled a break for 2:15, so you get an extra 5 minutes. So let's take a 15-minute break. We'll come back at about 2:25 and we'll make some other comments here about the other influence of sea level here, because you need to appreciate what sea level has been doing through the whole scene. It has a bearing on our styles of deposition. So let's take our break. We'll come back at 2:25, okay? See you then.